Now that we know everything there is to know about quadratic functions, we are going to look at higher degree polynomial functions. So by higher degree, we mean degree higher than 2. So the functions that we have so far are constant functions. So for example, like y is equal to 4. That's a constant function. It never changes. It just flat lines up there at 4. Then we have linear functions. And those have a degree of 1. So like y is equal to 2x plus 3. That's a linear function. Then our quadratics, 2x squared plus 3 maybe. Okay, so we have constant, linear, quadratic. Now we're going above second degree and looking at polynomial functions of degree 3 and higher. Okay, so first of all, polynomial functions are classified by their degree. All right, so y is equal to 2x cubed plus 3x. Okay, well this polynomial has degree 3 because the highest power on one of the variables is a 3. Because we have a 3 there, on the x we don't have an exponent shown, so we know it to be 1. So we don't add those together, we just take the highest one. So this has degree 3. The polynomial y is equal to x squared minus x to the 4th. The first term is degree 2, the second term is degree 4, so the polynomial is degree 4. And if the largest power that we see is a 5th power, then that's going to be a 5th degree polynomial. Okay? So we classify them by their degree. Characteristics of polynomial functions? Well, first of all, they are continuous, so we could draw the curve from the beginning to the end, like to the left to the right, using a continuous pen stroke. So, for example, like this. It's continuous. There are no breaks or gaps or anything in it. So we're not going to have piecewise functions. Those are not polynomial functions. Okay? So continuous means like that. We can draw it with our pencil without picking it up. And then another thing is it has smooth, rounded turns. Okay, so another example might be one that looks something like this. So an absolute value function is not a polynomial function. And a piecewise function is not a polynomial function, okay? But these two are examples of polynomial functions. The leading coefficient test, we only use it for finding the end behavior of a graph. It doesn't tell us anything about the inside, what's going on in the middle of the graph, whether the number of intercepts it has or how many turns, but the end behavior, eventually what happens to the graph. And the leading coefficient then, we need two things. It will tell us, we need to know the degree of it and what the value of the leading coefficient is. All right, and we will be able to tell eventually what happens to the graph as it goes to the right or to the left. Is it going up? Is it going down? So that's what we mean by end behavior. So for example, if we have a cubic, and a cubic is going to be the third degree, so that's an odd. So odd degree, we know that those polynomials have opposite end behavior. So a cubic could look like this, or it could just be doing the opposite thing and going up to the left and down to the right. Okay? If we have a fourth degree similar to that of a quadratic, has the same end behavior. So a polynomial that goes up to the left, eventually, you know, as you go to the left, it ends up going up. The same thing will happen on the right side. Both of the end behaviors are positive, or both of the end behaviors are negative, and those are on fourth degree or any even degree. Whereas odd degrees have opposite end behavior. Let's take the polynomial function then. I don't have a lot of room, maybe I'll use it in red. Let's say we have f of x is equal to x plus 2x squared minus x cubed. Okay, so this polynomial function is higher degree, so it's a cubic. Cubic or odd degrees have opposite end behavior. So I saw from the degree that it's odd, so therefore it has opposite end behavior. One side, as you go to the right, it goes up, the left down, or just the opposite. So then I need to look at the leading coefficient to tell me which of those two it is. So the leading coefficient in our case is the coefficient of the x to the third, or it's a -1. So that means as we go to the left, it's going up. So this particular graph might look something like this. Now, like I said, that polynomial function, just looking at this leading coefficient test, doesn't tell me that it has 3 zeros. I don't know that at all. Maybe it only has 2, maybe 1. But it could have up to 3. But what it does tell me is that eventually, as I go to the left on this graph, the end behavior is it's rising, it's going up, and eventually as I go to the right, it's going down. So that's all it tells me. It doesn't tell me all about the middle stuff. Real zeros. So in order to find the real zeros, we have our calculators that help us out so much, but we are going to take a look at where it crosses the x-axis. So let's say that I have this polynomial function. Let's just graph this in, and I can tell by looking at it then it's crossing here and it's crossing here. Okay, this has 2 real zeros. So the real zeros are where it crosses the x-axis. So when we talk about a zero, it's what makes, it's the value that we find where it crosses the x-axis. So if we're solving it, we're finding what the value of x is so that the y is 0. If a is a 0, so let's say this is a right here. A is a 0, meaning it makes the function equal to 0. That also means then that a is an x-intercept, that's where it crosses, that's at one point anyway where it crosses the x-axis. It is also referred to, so not only as a 0, but as a root or a solution to the equation. And if it's a solution or a root or a 0, then we know that a factor is going to be x minus a. Okay. If I have this curve, let's take this. Okay. So I can see that it's crossing here and here and here and here. So this particular function has how many zeros? Well, it has 4 of them. Let's say that this 0 here is A, this is B, this is C, and this is D. Okay, so I have 4 zeros. My x-intercepts are at A0, B0, come on, C0, and also D0. If I were to write that polynomial in factored form, my factors would be x minus A, x minus B, whoops, then I put the B first, x minus B, x minus C, and x minus D. And maybe some of you are thinking, oh, but those minus signs, like A is a negative number. If A then truly ends up being on that opposite side, then yes, you would have a negative number in there. So then the factor would look like x plus A, because it's to the left of 0 here. Where the others, because the roots are actually to the right of 0, they are going to remain negative. So it would look something like that. Okay, so from here you just need to know then that a lot of these things are asking the same thing, so that terminology is so important. So when we're talking about real zeros then, we are talking about solutions to the equation if we set it equals 0. We know then that's called a root. In your calculators, when you calculate it where it crosses the x-axis, it's known as a 0, but they are the x-intercepts, and from the x-intercepts, if we know that, then we can find the factors. Okay, so they're all related. They're not different disjoint things. Repeated zeros. All right, let's say we have a polynomial that has x squared as a factor, and let's go with x plus 2 as a single factor. Okay, so my repeated zeros are where we have the same factor raised to more than 1. So here the repeated zeros of this one are 0 and 0, whereas in the single 0 is negative 2. So these are called repeated factors, because that x squared means we have x times x, times x plus 2. So if you're repeating factors, you're repeating zeros. If we take f of x is equal to x minus 3 to the third, and then let's say we have an x plus 5 to the second. Well, both of these zeros are repeated. The 0 here, so remember when we talk about the zeros, it's what makes the y equal to 0, because we're looking for the x-intercept. So the only way we can get a 0 from these two factors is if one of them is equal to 0. So if I set the first factor equal to 0, then I see that x could be 3, or x could be negative 5. But they are, both of those are repeated zeros. Oh, yep, I just caught that mistake. That should be a 2, huh? I just changed that. This one, the 3, is a 0 3 times. It's repeated 3 times. But when we ask for the solutions or the root, you don't have to repeat it that many times. I might ask what's the multiplicity of it. So it would be multiplicity 3, because it's repeating 3 times. Whereas the negative 5 is repeating twice. But there are only 2 different real zeros. Okay? Now let's try sketching what the graph of that polynomial is going to look like if they are repeated zeros. Okay, so I have some with repeated zeros and I have some that are not. So on this first one, you should be able to tell me what the degree is. So we see that we have an x plus 2, that quantity raised to the third. So if I were to multiply it out, the highest power of x is going to be the third. Okay, so it's a cubic, so that's a higher degree. I see that it only has one zero. The only zero is at -2. Okay, so that means that's the only place that it is crossing the x-axis. Okay, a cubic function. We know that a cubic function then, as we go to the left, the end behavior is going down because my leading coefficient is going to be 1. So a positive 1, and then as it comes out, it's going to go up. So the end behavior. So it's going to look something like that. So if it's a repeated 0 3 times, it's actually going to cut through the axis. So it goes from below, from a negative value to a positive value. Or it could just be the opposite. Okay, on this next one, where we have a factor of x, x plus 2 and x minus 3, our zeros are 0 and positive 3 and also -2. These are not repeated zeros. These are single zeros. They only occur one time, and anytime they occur an odd number of times, it actually, when you go through the 0, you actually cut through the x-axis. So if you're above, you go below. If you're below, you go above. This one, once again, if we were to multiply it all out, it would be a positive 1x cubed. So a positive 1 is the leading coefficient. So to the right, it's going up, the end behavior. To the left, it's going down. And it actually cuts through. So it's going to rise here, it's going to come back down, it's going to cut through because it's a single 0, and then it's going to come back up here and cut through the axis. Okay, so that's a possible sketch. Here again, I don't know exactly how high it's going up or anything, but that gives me a fairly decent sketch of that graph. All right, now on this one, I repeated one of the zeros. So we have a 0 at -2, and we have a 0 at positive 3. Once again, if I were to multiply this all out, the leading coefficient would be a positive 1. So that means to the right, it's continuing up. To the left, the end behavior is going down. At the repeated 0, so the 3 is the repeated 0, and it's occurring an even number of times. When it's an even number, it doesn't cut through the axis, but it touches it and bounces back up. So we refer to that as being tangent. Remember from geometry, if a line was tangent to a circle, it means it intersected that circle exactly one time. Well, our curve is tangent in the same way to the x-axis. And then it comes back over here, and it catches up to the 0 of -2. So the curve might look something like that. On this last one, my zeros are 0 and positive 3. Okay, so the zeros, because the x is squared, I have a repeated 0 at 0, and then I just have a single 0 at 3. Okay, so a repeated 0, or we say it has multiplicity 2 at 0. At that point here, it's going to be tangent. The curve is going to be tangent to the x-axis. Once again, if I multiply this all out, we'd have a cubic. The leading coefficient is a positive 1, and behavior to the right is up, and behavior to the left is down. The one where the repeated 0 occurs an even number of times is its tangent. So here it comes up, and then it hits it and comes back down. And then over here, because it's a single zero or any odd multiplicity, it cuts through the axis at that point. Okay? All right, so that was a lot of information. Actually, not too long of a podcast, so about 20 minutes. So we will do some more of those. I'm sure you have some questions because we didn't do a lot of different ones. We just looked at cubic, so we still have quite a bit of work to do. In this, though, I just want to, give credit to our pre-calculus book that we use in college algebra. We use the pre-calculus text from Larson, and so I take the ideas and the thoughts, from that section to help with these podcasts, and that's because we use that book. So since we purchased the book, that's the material that we look at. So I want to make sure and cover everything that you might see there. All right, very good. See you in class.